Welcome my dear learners for this course on operations research. From today we are beginning module 3. In this module 3 we will be discussing on transportation problem and assignment problem. First let us discuss transportation problem in today's lecture. So in today's lecture we will be beginning the discussion on module 3. In module 3 we will be addressing on transportation problems. Transportation problem is a special case in linear programming problem. The aim is to transport homogeneous commodities from M origins to N destinations with total minimum transportation cost. Let us consider we have many origins like A1, A2, A3, etc. to AI, from which I want to transfer the homogeneous commodities to destinations B1, B2, B3, B4, etc. up to Bj. And we assume that from each origins I can transfer commodities to all the destinations. That is, I can transfer commodity to A1, A1 to B1, A1 to B2, A1 to B3, A1 to B4. Like that I can transfer commodities from all origins to all destinations. Now the aim is to determine with what minimum possible transportation cost I can satisfy the supply and demand. That is the aim of this transportation problem. From each source transferring the commodity to each destination, we might incur cost, that is C1, C2, C3, etc. We want to optimize this transportation cost. That is the aim of this transportation problem. So in case of transportation problem, the important criteria are the supplies from each origins, the demands at each destinations, and the transportation cost. So these three are the most important parameters to be considered in a transportation problem. So if I represent the transportation problem in a matrix form, the transportation problem matrix look like we have the source or origins, we have the origins, and we have the destinations. We have the destinations. Let us say we have the origins or the sources as source S1, S2, S3, etc. till Si. So S stands for source. And we have the destinations. Let us say the destinations as D1, D2, D3, D4, etc. up to Dj. Now we always represent the supply in column next to the last destination. We mark the supply, and at the bottom we always mark the demand or requirement, or the requirement will be marked here. So from each source we will be transferring the commodity to the destinations. Our aim is to determine what is the total minimum transportation cost. So always we represent the supply in column to the last destinations, adjacent to last destinations. Always we represent the demand in row below the last source. Now transferring this, we will be having the cost that is going to incur. Like from source S1, if I transfer a commodity to destination D1, the cost incur will be C11. Similarly we have C12, C13, like that I will get C1j. So similarly if I go, I will get CI1. Correct? So this is the representation of transportation problem in matrix form. Now as I already said, a transportation problem is a special case in linear programming problem. What is a linear programming problem? A linear programming problem is one which has objective function, either to maximize or minimize is the aim of the objective function, and it is subjected for constraints. Like that, the aim of the transportation problem is what? The aim of the transportation problem is to minimize the transportation cost. Correct? Let us consider Xij be the unit commodity to be transported from source to destination. Let X be the unit commodity that needs to be transported from ith origin to jth destination. So our objective function is to minimize the transportation cost. So therefore, what will be the objective function? Our objective function is always to minimize, right? I want to minimize what? The total sum that is going to incur in transferring the commodity from source to destination. So let C be the unit cost. So therefore Cij, and X is the commodity, right? Unit commodity is Xij, where I varies from 1 to m and j varies from 1 to n. So our objective function is to minimize the total transportation cost. So I formulated the objective function. So D subject to the constraints. What are the constraints we have? Subjected to. What are the constraints we have? The first constraint is that whatever commodity that leaves the origin, correct? Whatever commodity that leaves the origin, that is Xij, should be always less than or equal to the supply. Should be always less than or equal to the supply. Whatever there in the supply, so it should not exceed that, right? So Ai, that is for all I. So J should be 1 to n. What does it mean? Whatever the commodity that is leaving from the origin, that is should not be exceeding the supply. So we have 50 as the supply quantities present that can be leave the source 1. So whatever commodities that is going to leave from source 1 should not exceed the supply whatever quantity I have. That is the constraint number 1. Next is constraint number 2. That is whatever commodity that reaches the destination should be always greater than or equal to demand. Should be always greater than or equal to demand, where I is equal to 1 to m. Here, so whatever, so these are the B's, demands, and these are the supply, that is A's. So we have A1, A2, etc. up to AI, and we have demand, that is B1, B2, B3, etc. up to Bj. Clear? So if you, and also we should always have positive constraint, right? So always the commodity should be positive. Sum of all ij's should be greater than or equal to 0. This is the positive constraint. Now if you carefully look at this problem, we have formulated the objective function and we have formulated the constraints. A transportation problem is said to be unbalanced if we have constraints like this. What I mean to say is that if the sum of demand is not equal to the sum of supply, then such transportation problem is said to be unbalanced transportation problem. And also such unbalanced transportation problems will have constraints. They will not have equations. Whenever the supply, sum of supply is not equal to sum of demand, such problems are said to be unbalanced transportation problem. Such unbalanced transportation problem can be made into the balanced transportation problem by adding dummy column or dummy row. So therefore, this unbalanced transportation problem should be first converted into balanced transportation problem. A balanced transportation problem is one which has equations, and also for a balanced transportation problem, sum of demand will be equal to sum of supply. So this is the unbalanced transportation problem because we have constraints. Now if I made into equations, so if all commodities that leaves is equal to the supply and all commodities that enters is equal to the demand requirement. This is a positivity constraint, and also total supply is equal to total demand. If total supply is equal to total demand, so I varies from 1 to m and j varies from 1 to n. So this means to say total supply is equal to total demand. If total supply is equal to total demand, so then we have only equations instead of constraints. So such problem is termed as balanced transportation problem. So hope you understood the transportation matrix. What is that it contains? It contains source and destinations and the unit commodity cost. Always you represent the supply towards right as a column and demand at the bottom as row. And a transportation problem is said to be unbalanced if it has only constraints, it does not have equations, and also the sum of demand is not equal to sum of supply. A balanced transportation problem is one which has only equations in it, and also the total supply is equal to total demand. Now if I allocate the supply to the commodity from one source to one destination, so from one source to one destination, like that if I made allocations throughout this transportation problem, then the set of allocations what I make will reduce the deficiency. It is called as feasible solution. A feasible solution is nothing but the set of allocations which reduces the deficiency, and it is termed as feasible solution. If the number of allocations that I make in this transportation problem is equal to 1 less than sum of rows and columns, that is 1 less than sum of sources plus destinations, then it is termed as basic feasible solution. Now if the number of allocations what I made, if the number of allocations what I made is equal to m plus n minus 1, where m is the number of sources s1, s2, s3, let us say I have only 3 sources, and n is the number of destinations 1, 2, 3, 4 let us have, and also the transportation problem need not be having same number of rows and same number of columns. That is, I might have 18 students with me, I want to transport these 18 students to 9 schools. All these 18 students are coming from 18 different houses, so therefore the source are the houses of these children, right? So therefore how many sources we have? 18 sources. But how many schools? The destinations we have 9 destinations. So sources need not be equal to destinations, and destinations need not be equal to sources in case of transportation problem. Always keep that in mind. Now what is the least transportation cost with which I can transfer these 18 students from 18 different home to 9 school is the objective function of this transportation problem. So now we have m sources and n destinations. So if the number of allocations that I made is equal to 1 less than sum of sources plus destinations, then such solution is said to be basic feasible solution, and it is called as non-degenerate basic feasible solution. If the number of allocations is equal to m plus n minus 1, where m is the number of sources and n is the number of destinations, then such solution is called as non-degenerate basic feasible solution. If the number of allocations is not equal to, means if the number of allocations is less than m plus n minus 1, if it is less than m plus n minus 1, then it is called as degenerate basic feasible solution. So this is the important basic introduction about transportation problem. Now, in case of transportation problem, we will be solving the transportation problem in 2 steps. In step 1, we will be determining the basic feasible solution. That is, we will do some allocations by using some techniques, and will reduce the deficiency of the transportation problem, which is nothing but the feasible solution. It might be basic, it might not be basic feasible solution. It might be non-degenerative or degenerative basic feasible solution. Now, we will do the optimality test for the initial basic feasible solution what we have obtained to get the optimum cost for transportation. So, therefore, the transportation problem will be solved in 2 different steps. In step 1, we will be determining the basic feasible solution. In step 2, we will be checking the optimality test for the previously obtained feasible solution. To obtain the feasible solution for any given transportation problem, there is 3 popular techniques that we are going to employ. First one is northwest corner method, second one is matrix method, or it is also called as least cost matrix method, and third one is Vogel's approximation method. So, using these 3 methods, we can determine the basic feasible solution for any given transportation problem. Next, once we obtain the basic feasible solution for the transportation problem, then we will be using the optimality test either by using stepping stone method or by using modified distribution method. That is, we have now our aim is to find the optimal solution to transportation problem. Now, to find the optimal solution to transportation problem, in step 1, we will find the initial basic feasible solution So, the methods that can I employ to find the initial basic feasible solution are, first one is northwest corner rule, northwest corner method or northwest corner rule. Next, we have matrix minima method, which is also called as least cost entry method. And finally, we have the popular Vogel's approximation. Vogel's approximation method. Vogel's approximation method is also called as unit cost penalty method. So, using any one of these 3 methods, we will be finding the initial basic feasible solution, and in step 2, improve the basic feasible solution to get optimal transportation cost. So, we have 2 popular techniques to improve the basic feasible solution. One is stepping stone method and another one is modified distribution method. Which is popularly called as Modi method. So, this is how we will solve the optimum solution for a given transportation problem. First, we will use any one of these methods to find the initial basic feasible solution. Then, using any one of these 2 techniques, we will improve the previously obtained basic feasible solution to get the optimum transportation cost for any given problem. Now, let us take a simple example and discuss all these three techniques and observe what is that the difference that I am going to get in the initial basic feasible solution and why is it so. Let us discuss that in today's lecture. Now we have the problem number 1 as find the initial basic feasible solution to the following transportation problem in which the cells contain the transportation cost in rupees. We have the source F1, F2, F3, F4 and we have the destinations W1, W2, W3, W4, W5. You can observe the number of sources is not equal to the number of destinations. No need to worry about that, leave it. The first step is to verify whether it is a balanced transportation problem or not. A balanced transportation problem is one in which the sum of demand should be equal to sum of supply, right? How much is the supply or availability? So availability is turning out to be 40 plus 30 plus 20 plus 10, which is 100. How much is the demand? 30 plus 30 plus 15 plus 20 plus 5, 100. So supply is equal to demand. So therefore this is a balanced transportation problem. If it would have been an unbalanced transportation problem, then in such cases you should add dummy row or dummy column. Means what? The unit transportation cost of a dummy row or dummy column is 0, 0, 0 and add the deficient demand or deficient supply appropriately such that the sum should be equal to, the sum are equal, supply should be equal to demand. Whereas in this case the availability is 100 and demand is also 100, so therefore this is a balanced transportation problem. So since it is a balanced transportation problem, we can go for the solution. So in solution, first step we should find sum of availability should be is equal to sum of requirement. Therefore this is balanced transportation problem. Balanced transportation problem. If I got availability as 100 and demand as 90, I have 10 deficiency in demand, so therefore add one more column of 0, 0, 0, 0 and write it 10 here so that the sum will become 100. If I have 100 as the demand and 90 as the supply, then 10 is deficient in supply, so then add dummy row, write it as 0, 0, 0, 0 and write 10 here such that we made it as a balanced transportation problem. Always in first step ensure that the transportation problem is balanced. Now it is already a balanced transportation problem, no need to worry much. So first let us address the problem by using northwest corner rule. Northwest corner method. NWC stands for northwest corner method. So in case of northwest corner method, always we will start from the northwest corner and proceed the allocation. So we have the directions as north, south, east and west. So this is the northwest corner, correct? Always you should start from the northwest corner for the problem and start the allocation, right? So first let us rewrite the given problem such that the cost should be written at the northwest corner unit cost and then we will make the allocation. So first we have 7, then we have 6. So write this in the northwest corner of each cell, the unit cost. Next we have 4, next we have 5, next we have 9. So similarly write down for remaining rows. We have 8, 5, 6, 7 and 8. Then we have 6, 8, 9, 6 and 5 as the unit cost, and finally we have 5, 7, 7, 8 and 6 as the unit cost. Done. Now note down the supply units as 40, 30, 20 and 10. Also we have the demand or requirement as 30, 30, 15, 20 and 5. Right. So now start from the northwest corner of the entire matrix. So northwest corner is this one, correct? So the northwest corner, the first northwest corner is what? So the northwest corner is x11, x11. So there you allocate minimum of row comma column. Row is how much? Minimum supply is 40 and demand is 30. So minimum among supply and demand, supply and demand is 30, supply is 40. So minimum is how much? So minimum is 30, that is demand. So allocate minimum. So demand is the minimum. I have allocated 30. So since 30 is already allocated, nothing is remaining. So since I allocated 30, supply I have taken 30. So now supply remaining is only 10. Clear? So this is first step. Now in the remaining matrix, identify the northwest corner. So in the remaining matrix, the northwest corner is this one. So therefore the northwest corner is first row, second column. So there the minimum of 10 is the supply and demand is 30. So therefore if I allocate to x12, minimum is 10, so therefore allocate 10. So since I have allocated, nothing is remaining. So since I already allocated 10 here, so the remaining will be now 20. So 10 is already allocated, remaining is 20. Be careful, this you should not skip. Already 10 has been allocated, so now the requirement will become only 20. Now move ahead in the remaining, which is the northwest corner. So this is the northwest corner, that is the next northwest corner is x22. So minimum of supply is 30 and demand has now reduced to 20. So minimum is 20, right? So allocate 20 here. So since I allocated 20 here, now the remaining will become 10. So x22 is equal to 20. So now the remaining, which is the northwest corner, this is the northwest corner. So northwest corner is x23, second row, third column. So allocate minimum of 10 and 15. Minimum among 10 and 15. 10 is the minimum. I will allocate 10. So this is eliminated. Since I allocated 10, now the remaining is only 5. So x23 is equal to 10. Now in the remaining, which is the northwest corner, so this is the northwest corner, that is 3, 3. So now the northwest corner is x 3, 3. So allocate minimum of 20 and 5. 20 and 5. So therefore x33 will get 5. So therefore this will be eliminated. Since I already allocated 5, now the remaining is 15. Now the northwest corner will be, x34. So minimum of supply is 15, demand is 20. So therefore x34 will be 15. So this is eliminated. Since I have taken 15, only 5 is the remainder. So next northwest corner is this one. Next northwest corner is x 4 comma 4, so minimum of supply is 10, demand is 5, so x 4 comma 4 will take 5, it will take 5, so this is eliminated. Since I taken 5, only 5 is the remainder, so therefore final allocation will be 5. Final allocation will be 5. We don't have any choice, it is forcing us to allocate 5. Now we multiply the basic feasible solution. How much the transportation cost? The total cost will be equal to 30 into 7 plus 10 into 6 plus 20 into 5 plus 10 into 6 plus 5 into 9 plus 15 into 6 plus 5 into 8 plus 5 into 6. So totally we have 1, 2, 3, 4, 5, 6, 7, 8 allocations. Totally we have 8 allocations. So this is an 1, 2, 3, 4. 4 cross 5. So it is a 4 cross 5 matrix. So M is 4 and N is 5. 4 plus 5 is 9. 9 minus 1 is 8. So number of allocations is also equal to 8. So number of allocations is equal to M plus N minus 1. So therefore this is a non-degenerate basic feasible solution, which we already discussed. If the number of allocations is exactly equal to M plus N minus 1, then it is called as non-degenerate basic feasible solution. So here we have number of sources or origin as 4, number of destinations as 5. So 4 plus 5 is 9, minus 1 is 8, and the total number of allocations is also equal to 8. So therefore it is a non-degenerate basic feasible solution, and the total cost is turning out to be, so he is stating that the costs are in rupees, so therefore it is rupees 30 into 7 plus 10 into 6 plus 20 into 5 plus 10 into 6 plus 5 into 9 plus 15 into 6 plus 5 into 8 plus 5 into 6. 30 into 7 plus 10 into 6 plus 20 into 5 plus 10 into 6 plus 5 into 9 plus 15 into 6 plus 5 into 8 plus 5 into 6. It is turning out to be 635 rupees. So the initial basic non-degenerative feasible solution is turning out to be the total cost of rupees 635. Let me pause this video for a while so that people can copy it down. Later we will solve the same problem by using least cost entry method or matrix minima method. Now moving ahead, let us solve the same problem by using matrix minima method. In northwest corner rule, we got the total cost as rupees 635. Now let us solve the same problem by using matrix minima method. Or least cost entry method. Now for matrix minima method, let us rewrite the given problem once again. As I said, we have 7, 6, 4, 5 and 9. Then we have 8, 5, 6, 7 and 8. Then we have 6, 8, 9, 6, 5. And finally we have 5, 7, 7, 8 and 6, right? Also note down the supply and demand: 40, 30, 20, 10. Here we have 30, 30, 15, 20 and 5. In case of matrix minima method, identify the least unit cost in the entire matrix and allocate it first. Likewise, you keep moving from one least cost to next least cost, next higher least cost, next higher least cost, and keep allocating until you finish off the required number of allocations. Now, if I carefully observe this, the least unit cost is 4, correct? So allocate for this first. So now for this, if I move for allocation for this least unit cost 4, so it allocate minimum of 40 and 15. So minimum is 15. I will allocate 15 here. So this is gone. Remaining is how much? Remaining is 25, correct? So next least cost is 5. I have here, here, here and here. We have tie between 5. Whenever you have a tie, you can break the tie arbitrarily. There is no hard and fast rule that you should solve like how I am solving. Whenever there is a tie, you can break the tie arbitrarily. You can go and allocate here, or you can go and allocate here, or you can go and allocate here. Let me use some procedure so that I'll use the steps properly. So I'll use row preference. So I'll go with the first row. So 5 I have here. So minimum of 25 and 20. So minimum of 25 and 20 is the minimum. I'll allocate 20 here. So no allocation is possible further. So I'll make it as 5 is the remaining thing. Next I have 5 here. So minimum of 30 and 30. Minimum of 30 and 30 is 30. So no allocation is possible. And here also no allocation is possible. So 30, remaining will be 0. Next, I have 5 here. Minimum of 20 and 5. So 5 is the minimum. So this is gone. No allocation is possible further here. So I have taken 20. Remaining is 15. Next, I have 5 here. So minimum of 10 and 30. Minimum is 10. So no allocation is possible further here. So I taken 10. Remaining is 20. Clear? So now I left out with 3 more possible allocations with 5, 15 and 20. Now next least cost is 6. No allocation is possible. Over. Here also over. Here also over. Only possible is here. So minimum of 20 and 15. Minimum of 20 and 15 is 15, right? 15. So no allocation is possible further. 15 is gone. So remaining is 5. Remaining is 5. Now we are left out with only 2, 5 and 5, and we have only one point to allocate, that is here. So allocate 5. So this is also gone and this is also gone. Now compute the total cost. Now if I compute the total cost, we have five into 7 plus 15 into 4 plus 20 into 5 30 into 5 and then we have 15 into 6 and then we have 5 into 5 and then we have 10 into 5. So if you look at here, we have totally 7 allocations, which is less than m plus n minus 1, which is less than m plus n minus 1. So therefore the solution will be degenerate feasible solution, because the number of allocation is 1 less than m plus n minus 1. So we have 4 sources, 5 destinations, 4 plus 5 is 9, 9 minus 1 is 8, but the number of allocations are 7 here. So let me find out how much is the total cost in the initial basic degenerative feasible solution. The total cost that I am getting is 5 into 7 plus 15 into 4 plus 20 into 5 plus 30 into 5 plus 15 into 6 plus 5 into 5 plus 10 into 5, which is turning out to be rupees 510. So in case of northwest corner rule, we got rupees 635, whereas in case of matrix minima rule, we are getting 510. Why this difference is happening? And also, if you carefully observe, the minimum cost obtained is in case of matrix minima method. This is because of the reason, in case of northwest corner rule, we are not giving preference for the unit cost. We are neglecting the unit cost, just we are moving from northwest corner to complete the allocations. But here, we are carefully taking the unit cost into account and then we are allocating. So therefore, it is expected in the initial stage itself that matrix minima method should give better answer when compared to the northwest corner rule, and it is obtained so. In northwest corner rule we got rupees 635, whereas in case of matrix minima method we got rupees 510. So matrix minima method gave us the answer as rupees 510. And this is not the optimum cost. This is just initial basic feasible solution that we are determining by using 3 different techniques. One among these will be taken and improved for the optimality test. Now let me pause this video for a while so that you people can copy it down. Later we will address the final initial basic solution technique, that is Vogel's approximation method. Now moving ahead for the final initial basic feasible solution technique, that is Vogel's approximation method. So moving for Vogel's approximation method or least cost penalty method, it is also called as Vogel's approximation method. So in case of Vogel's approximation method, we will be allocating based on the penalty. Penalty is nothing but the difference between the second least cost and first least cost. What I mean to say is that if I am unable to transport with the least unit cost possible, what is the penalty that I am going to pay for that, because of not transporting with the least possible cost. So based on that, we will be allocating the allocations from source to destinations. So penalty is defined as the difference between the second least cost and the first least cost. Come, let us discuss and solve the given problem using Vogel's approximation method. Vogel's approximation method is based on penalty, so therefore I should calculate the penalty for both row as well as column. So for which, let us formulate for step 1. So let us take step 1 and write it in the form of, let me keep it as earlier so that we will use the same procedure. So northwest corner I will write the unit cost as it is 7, 6, 4, 5, 9, correct? And then we have 8, 5, 6, 7 and 8, and then we have 6, 8, 9, 6, 5. 6, 8, 9, 6, 5. And finally we have 5, 7, 7, 8 and 6. So here we have supply, that is availability, as 40, 30, 20 and 10. Here we have the requirement as 30, 30, 15, 20 and 5. Now let us calculate the penalty, and here also I will calculate the penalty. As I said, penalty is the difference between second least cost and the first least cost. So in the first row, the second least cost is 5, first least cost is 4, 5 minus 4 is 1. Here second is 6, first is 5, 6 minus 5 is again 1. Here also we have the same thing, penalty is 1. Here we have 5 and 6, penalty is 1. Coming over this column, 5 and 6, penalty is 1. Here 5 and 6, penalty is 1. Here we have 4 and 6, 6 minus 4 is 2, penalty is 2. Here we have 5 and 6, penalty is 1. Here we have 5 and 6, penalty is 1. So highest penalty is this one. So therefore I should allocate for this first. So now the least cost among this is 4. So for this, the minimum of 40 and 15 is what I should allocate, right? So minimum of 40 and 15 is 15. Minimum of 40 and 15 is 15. So this is eliminated, and remaining is how much? 25. 25. Done. Now for the remaining thing, you calculate the penalty. Now for the remaining thing, you should calculate the penalty. So now for the remaining thing, if I calculate the penalty, it is a difference between 5 and 6. Again the penalty is 1. So this is penalty for the step 2. This is for the penalty for step 1. Penalty for step 2 is 5 and 6 is again 1. Here we have 5 and 7, penalty is 2. Here we have 5 and 6, penalty is 1. Here we have 5 and 6, penalty is again 1. Now in this column we have 5 and 6, penalty is again 1. In this column we have 5 and 6, penalty is again 1. This is already eliminated. Here we have 5 and 6, penalty is again 1. Here we have 5 and 6, penalty is again 1. Whenever there is a tie between penalties, you can arbitrarily break the penalty. There is no rule to break penalty. Arbitrarily you can break the penalty. Keep that in mind. Now the highest penalty is here. So therefore I should eliminate this one. Now the minimum cost is here 5. 5 is the least cost. Minimum of 30 and 30. So 30 is the minimum. 30 is the minimum. So therefore I have eliminated this one. So since I have only 30, already 30 is allocated, no further allocation is possible, right? No further allocation is possible because nothing is remaining here. Next, calculate the penalty in step 3. Calculate the penalty in step 3 for the remaining thing. So we have 5 and 7, penalty is 2. 7 minus 5 is 2. Here it is already eliminated. Coming over here, we have 5 and 6, penalty is 1. Coming over here, we have 5 and 6, penalty is 1. Now in the column, so it is unchanged, 1, 1 and 1. Right? Correct. Now the highest penalty is for the first one. So therefore I should eliminate this one. In the remaining, the least is here 5. So minimum of 25 and 20. Minimum of 25 and 20. So 20 is the minimum. So I left out with 5. So eliminate this one. Now again calculate the penalty for the remaining thing. We have 7 and 9. Penalty is 2. We are moving to 4th round. Penalty is 2. Eliminated. Here we have 5 and 6. Penalty is 1. Here we have 5 and 6. Penalty is 1. So in the column, penalty is 5 and 6. Penalty is 1. And we have 5 and 6. Penalty is again 1. Now the highest is again here. So we have 5. Minimum is here 5. So this is eliminated. Since I have taken 5, remaining will be 25. Remaining is 25. We have left out with 2 rows and 2 columns. So if you carefully observe, 5 minus 6 penalty is 1, 5 minus 6 penalty is 1, 5 minus 6 penalty is 1, 5 minus 6 penalty is 1. There is a tie. So you can break the tie arbitrarily. So let me use the minimum cost first. 5 is here and it is a minimum of 20 and 5. So I allocate 5. So this will be eliminated. Remaining is 15. And then I have minimum here 5. So minimum of 10 and 25. 10 is the minimum. So I will eliminate this. Remaining is 15. So now 15 will go here. Hope you followed. First you calculate the penalty. Highest penalty you give the preference. So take the least unit cost among that particular column or particular row which you are addressing, and then you allocate there the minimum of availability and requirement. Eliminate respective row or column. Next, with the remaining thing you calculate the penalty. Repeat the same procedure. Whenever there is a tie, like in the last step we got a tie, 6 minus 5 is 1, 6 minus 5 is 1. Vertically also 6 minus 5 is 1, 6 minus 5 is 1. Correct? So we have a tie in all the 4, 2 rows, 2 columns. So break the tie arbitrarily. So therefore first I go with the row, minimum is 5 here. So for this the minimum among 20 and 5 is 5. So I allocated 5, eliminated, remaining is 15. Next least cost is here 5. So minimum of 10 and 30, minimum is 10. So therefore I eliminated, remaining is 25. Out of 25, 10 I taken, remaining is 15. Now 15 cross 15 will come over here. Done. Allocations are done. Hope you followed. So this is the 4th step penalty. Penalty in 4th step. So we have penalty of first step, second, third and 4th step. So in the 5th we got tie, so therefore I broke it arbitrarily. Now I have done the allocation. Let me calculate how much is the total cost that I am going to get. So total cost will be how much is the total cost? Total cost will be 5 into 7 plus 15 into 4 plus 20 into 5 plus 30 into 5 plus 15 into 6 plus 5 into 5 plus 10 into 5. So from Vogel's approximation method, I am getting the total cost as 5 into 7 plus 15 into 4 plus 20 into 5 plus 30 into 5 into 5 into 7, 15 into 4 plus 20 into 5 plus 30 into 5 plus 15 into 6 plus 5 into 5 plus 10 into 5. So I am getting the answer as rupees 510. So I am getting the answer as rupees. So for this also I am getting the answer as rupees 510. So if you carefully observe the among three methods, matrix minima method and Vogel's approximation method will give better answer compared to northwest corner rule. This is because of the reason northwest corner rule does not account for unit product cost, unit commodity cost, whereas matrix minima method and Vogel's approximation method give preference for the unit product cost. And furthermore, Vogel's approximation method is based on the penalty approach, so therefore this gives much better result compared to these two. So this is how we will be using any one among these three methods to find the initial basic feasible solution. Then using the optimality test either by using stepping stone method or by using modified distribution method will be determining the optimum transportation cost. That's all from this lecture. Thank you all.